Physical Geology, Chapter 9, Earthquakes and Earth's Interior, presented by Khalil Amrouni, PhD in Geology from Texas A&M. Khalil Amrouni is a staff member at the Department of Earth Sciences, Gayunus University, Benghazi City, Barga State, or Cyrenaica State. The reference used here is Essentials of Geology. This is the Department of Earth Sciences at Gayunus University, and this is the main interest of Gayunus University. This is the Prince of Barga State or Cyrenaica State, Idris Sunusi, and the founder of Gayunus University. This is the flag of Cyrenaica. Behind the Prince trees, this is the capital of Cyrenaica State, Benghazi City. This is the chief commander of the Sunusi army, Omar al-Mukhtar, and this is the map of Barga State or Cyrenaica State. Outlines of the earthquakes and Earth's interior. What mechanism does produce a destructive earthquake? Crustal uplifting, subsidence, horizontal movement. We'll go through the seismology, seismograms, two main groups of seismic waves, surface waves and body waves, and the body waves is divided. They're divided into two primary waves, call them P waves, and secondary waves, we call them S waves. Waves methods of travel or methods of propagation. P waves, they travel through push and pull or compress and dilate style, and S waves through shaking the particles up and down. Location of earthquakes, intensity and magnitude, the Earth's interior for major layers, crust, mantle, outer core, inner core, the Mohs discontinuity, the shadow zone, asthenosphere, lithosphere, composition of the continental crust, granitic, made up of granitic rocks, and the oceanic crust, made of basaltic rock. Okay. Earthquakes and Earth's interior. Here there's some news. Earthquakes are estimated by nearly 1 million earthquakes occur yearly. An earthquake is the vibration definition. An earthquake is the vibration of the earth produced by rapid release of energy. So, Earth's vibration and release of energy. This energy radiating in all directions from its source. What's that source? The focus. We call it the focus. The focus ringing like a bell motion. What's the focus? The focus is the source of an earthquake. We'll see it in the picture figure. It's in the the focus is the source of an earthquake. It's in the form of waves similar to those produced by a bell windstroke, vibrating the air around it. Consolidate earth materials imitate quicksand during the earthquake. Let's look at it here. So we have a fault line, and along the fault line, that's the fracture zone, but it has displacement, so we call it fault. Along this fault line, the energy released, an earthquake happened. And the weakest point here, along this fault line, we call it the focus, which is the main source of or release of the energy when the fracture and the displacement happen. So the focus, we call it Hypocenter, below the earth. The representation of this focus at the surface, their surface, we call it epicenter. And these reddish circles represent the distribution of the seismic waves. So here we have epicenter and hypocenter, which is the focus. Okay. Earthquakes and Earth's interior. What mechanism does produce a destructive earthquakes? We have crustal uplifting, subsidence, or horizontal movement of the Earth's crust or lithosphere. And always, these movements, uplifting or subsidence or horizontal movements, are frequently associated with large fractures with displacement. We call them faults. And based on the plate tectonics theory, the plates interact with each other, straining and deforming rocks at their edges. And along these plates boundaries, most of the earthquakes occurred. So most of the earthquakes occurred along the Earth's boundary. So what's the mechanism of the earthquake? Rocks are bending and storing elastic energy. Eventually, the friction resistance holding the rocks together is overcome. And then what happened? Slippage, which is the fault, occurs at the weakest point that we call the focus under the surface. And then displacement will exert stress further along the fault, where additional slippage will occur until most of the build-up strain is released. And we have after shocks and foreshocks. We'll look at the picture to see it, or the figure to see it better. So here, this is the original position of the Earth before the fault, and this is the representation is the stick. So when you bend the Earth as if you are bending a stick, what happens here? A lot of energy that you exert will stored in the stick. The same thing, this energy when the Earth is moved, is placed up, or this part is placed down, or the movement happened, horizontal movement, the rocks will be moved from the original position and start bending, and the energy will be stored inside the rocks until what happens? And this and this, this deformation, we call it elastic deformation. And then when the strength of the rock is overcome, or the friction force of the rock is overcome, the same example here, when you bend the rocks too much, or bend the stick too much, the strength of the stick will be overcome. The same thing happens here over time. The strength of the land will be overcome and then fractured, like here, fracture or rupture happen, which is, we call it fault zone. During that time, the energy will be released. The released energy that was stored in the rocks will cause the earthquakes and the vibration, which is wave vibration, and cause the movement of the Earth. And then the Earth tried to go back to the normal position, snap back. But that will happen in a different location because the Earth is already ruptured and moved to different location. During the earthquake, we'll have aftershocks and foreshocks. The foreshocks, these earthquakes, small earthquakes, happen before the major earthquake. The aftershock are the earthquakes that happened after the major earthquake, and they happen when the rock trying to adjust back to their return to their original position. Here we can see the fence due to the horizontal movement. It's split apart, or there's an offset of 2.5 meters away from each other. And that's a proof of the horizontal movement. Earthquakes and waves. So here we'll go and see seismology. Seismology is the study of earthquake waves. And then we have seismographs and seismograms. What seismographs are? The instruments, so the machines which record earthquake waves. The whole machine is called seismograph. Seismogram are the records of the seismographs. So the records or the papers, which we call them seismographs. They provide a great deal of information about the behavior of seismic waves. Seismograms, the records, reveal two main groups of seismic waves that that are generated by the slippage of a rock mass, which is earthquakes. The first group, we call it surface waves. They travel along the outer layer of the Earth. So surface waves, they travel along the outer layer. Body waves, second group, travel through the Earth's interior. And the body waves can be divided into two groups, primary or P waves and secondary or S waves. And the two waveforms are divided by their methods of travel or method of propagation. If we looked at P waves, they travel through push and pull or compress and dilate rocks. When they go through the rocks, they push and pull or compress and dilate rocks in the direction of the travel, where the wave travel. S waves, they shake particles at right angles along to their direction of travel. So we'll see that in a figure. So let's go through the seismograph. Seismograph is the whole machine here. It's inside this hole or well. This is the zoom in. And the machine is fixed with screws to the ground, the bedrock, hard bedrock. And the machine is made of wire, pivot, support, and suspended weight. And then here the pen and here the record, which is the seismogram. Okay? That records all the tremors or the movements of the Earth. Okay, earthquakes and waves. Here we have notes that P waves or the propagation of P waves involves changing the volume and shape. So P waves, when they move through bodies, they change volume and shape, while S waves, they change only the shape. That means P waves can travel through solid and liquids, while S waves can travel just through the solids, because fluids will not transmit S waves. Now we'll go to the other, this is about the body waves, P waves and S waves. So P waves, faster, they go through solid and liquid. S waves, slower, they're fast, but slower than P waves, and they go just through hard bodies, not through liquids. The surface waves, the third type, waves travel along the ground on the surface, not through the body of the Earth. And they can move up and down or side to side, the motion. Okay? And any, seismic record or seismogram will show the differences between the seismic waves. Will show you the 3 seismic waves. And by using the seismic waves, S waves and P waves, the travel time of S wave, the difference in travel time between S waves and P waves, it'll be very easy to determine the location and magnitude of the earthquake. And also, these seismic waves had been used to understand the Earth's interior. Okay, let's look at the seismogram. Seismogram shows me first group of waves here, small waves. So the first spike here, this is for P waves. And then as you move, this is the time, the difference between each line and the next is time. So here early time and here late time going this way. As you go along, you see another spike, but larger waves. We call them S waves. See how many minutes from like 1, 2, 3, 4. So P waves arrive at first to the station, and then after 4 minutes, S waves arrive at. And then if we keep going 5, 6 minutes, and you see another spike for bigger waves, which are the surface waves. They are slower than P waves and S waves. So the first spike here, the first arrival, or the first wave arrived to the station from surface waves. So P waves arrive first, second S waves, those two body waves arrive before, and then the surface waves, they arrive last. Okay, so here there's a seismogram showing P waves arrived first, and then after 1, 2, 3, 4, 5, 6 minutes, S waves bigger in amplitude, and then 7, 8, 9, 10 minutes, surface waves arrive at, and then so the body waves, P waves and S waves arrive to the station first. Seismogram record them first, and then the last thing, surface waves. P waves and S waves, we call them body waves because they travel through the body of the Earth. The surface waves, we call them surface waves because they travel along the Earth's surface. They don't go down to the body of the Earth. Okay, here is basically the plate tectonic boundaries, and these plate tectonic boundaries are the same zones of plate tectonics. They're tectonically active, and they're the same zones of seismic activities. Say maps. Let's go here, show you here. So mid-oceanic ridges, here subduction zones, and here mountain buildings, Himalaya and Alps. Okay. And here this figure showing me types of body waves that travel through the Earth's interior, which is P waves and S waves. P waves, when they move through any rock, they expand, compress through the direction of the wave's movement, okay, or the direction of propagation of the P wave. S waves, they go up and they shake the particles up and down perpendicular to the direction of propagation or direction of travel. So this is the main difference between P waves and S waves. P waves faster, S waves slower. This is about the body waves. If we go to the surface waves, they either roll up and down, or they go side and side. And those waves that causing earthquakes. Okay, location of earthquakes. How could we find the location of earthquakes? So we have to find the focus. The Earth is, focus is the place where the earthquake is originated and located under the surface. What's above the surface, not the focus, is the epicenter. We call it the epicenter. Okay, how could we find the location of an earthquake? The difference in the speed between P waves and S waves can help us to determine the location of any earthquake. But we have to use 3 stations. So what we do, we use a seismogram that has P waves and S waves recorded, and we use a travel time graph. So for example, we have station number 1 here, seismogram. Seismograph is the machine. So this is the seismogram. It has P wave, S wave, surface waves. This is the epicenter, the hypocenter, which is the focus. So this is the closest. All the 3 waves arrive. You'll find here 1, 2, in 2 minutes the P wave arrived. But here, farther away, 1, 2, 3 minutes. Took longer time for the P wave to arrive. Here, if you look at this station here, 1, 2, 3, 4, 5 minutes for the P wave to arrive. But S waves and surface waves not arrived yet. They are slower than the P wave. So those 3 seismograms from 3 different stations recorded the P waves and S waves travel time. When we get the P wave and S wave travel time, so we need to measure the difference in the travel times. This is the travel time graph. It has a time on the y-axis and it has the distance in kilometers from the epicenter. So once we got the seismogram, this is seismogram, so these smaller P waves, the first P wave, and here the first S wave, when they fit, we measure the time, which is 5 minutes. Okay, and here 5 minutes time and the distance, just you go down and read the number here. This is the distance to get a time difference, 5 minutes between the rival, 5 minutes between P wave and S wave. That means you are almost 4,000 kilometers away. 4,000 kilometers. This is the distance. Difference in time, 5 minutes. Just project it down here. That means you are almost 4,000, like 3,800 kilometers away from the epicenter. So what you do, these for 3,800, this is the diameter of the circle that you will draw around each recording station. So for example, from Paris, we have, let's go to this one. This is in Asia, in the Indian continent. The station, the difference, we got the difference between the P wave and S wave was like less than 5 minutes, which is almost 3,400 kilometers. We read it from here. And then this 3,400 kilometers is the diameter of the circle that will draw along this station. And we have another station from Paris. We draw, which is 8,200 kilometers, recorded the event, the seismic waves. And then we'll have this 8,200 kilometers as a radius for the other circle. And then we got another one from Australia, from station, recorded the distance to the earthquake was 4,900 kilometers, which is the diameter. We draw another circle. When these 3 circles intersect, this is the epicenter of the earthquake. So this is the location exactly above the focus of the earthquake. So this is how we determine the location of the earthquake. Okay. Earthquake's intensity and magnitude. Magnitude is the total amount of energy released during an earthquake. The magnitude is determined by how we do it, measuring the amplitude of the largest wave. So if we go back here, so here we have P waves, S waves, and surface waves. So the largest amplitude for S waves from here, from the horizontal to here, that's the largest amplitude. That's how we measure it. So measuring the amplitude of the largest wave. This is how we find out the magnitude. Recorded on the seismogram, which is the one just I showed you right now. So earthquakes vary enormously in strength. Okay, if the strength is their strengths are different, so consequently the wave amplitude generated vary by a factor of thousands or 1,000 times as well. To accommodate this wide variation, Richter used a logarithmic scale to express magnitudes. Okay, so Richter's scale for earthquakes is a logarithmic scale. On this scale of Richter scale, a 10-fold increase in wave amplitude corresponds to an increase of 1 on the magnitude scale. So here, each unit of magnitude increase on a Richter scale equates to roughly 30-fold increase in energy, in the energy released. Okay. And here's the equations to prove that. Earthquakes, intensity and magnitude. Richter scale is used worldwide to describe earthquakes magnitude. The largest earthquake ever recorded have Richter magnitude of nearly 8.6. This great shock released energy roughly equivalent to the detonation of billion tons of TNT. Earthquakes of less than 2.5 are usually not felt by human. Okay. What destruction caused by seismic vibration, tsunami and fire? So here the energy released by the earthquake travels along the Earth's surface. It causes the ground to vibrate in a complex manner. It moves up and down and from side to side, those surface waves. Tsunami. They, caused by seismic sea waves or tsunami. A lot of earthquakes in the oceans. Some people they were thinking tsunami, they are tidal waves, which is completely inaccurate. Most of the tsunamis are resulted from vertical displacement of the ocean floor during earthquakes, and we'll see that in the figure. Fires always associated with earthquakes and could be very destructive. So earthquakes may be predicted by what? How could we predict them? By regular monitoring ground tilt, fault movement, and seismic activity. If we monitor the seismic activity, we can predict the earthquakes when they'll happen. Here there's a scale for, like we call it intensity scale. So from 1, 2, 3, the intensity, 4, 5, intensity of earthquake. 6, 7, 8, 9, 10, 11, 12. What about earthquake grade 1? Not felt, except by a very few under special favored circumstances. Here, too, can be felt by few people, especially in the upper floors of buildings. For example, go 1, 2, 3, 4, 5. Go to 7. Everybody runs outdoors. Damage negligible in building of good design and construction. Slight to moderate in well-built ordinary structure. So they feel it. But like if you go to the last one here, damage total, waves seen on the ground surface. So people can't see the waves, the earth shaking up and down. Objects thrown up into the air. So here's look at the seismic waves in Santa Cruz. So here intensity very high. Here 2, 3, 4, scale 5, scale 6, scale 7, scale 8. So they map them. They find them there. The highest scale 8 here, as you go farther, 7, 6, 5, 4, decreasing the intensity of the damage of the earthquakes or the earthquake waves. So as you come closer to the epicenter, the intensity of the earthquake increased. Here determining the Richter magnitude of the earthquake. If we look here, we have amplitude, we have distance. So these two, we can find them from the seismograph. This is a seismograph. How to find the distance? We have P waves and S waves. And the distance here between them, 24 seconds. So just plot it on the distance. 24 seconds, which is almost 200 something distance in kilometers. Amplitude, the largest one, about 23 millimeters in this way. So plot the 23. If you connect this dot with this dot, they go through and intersect the magnitude. So the magnitude here is about 5 in Richter's scale. This is a way how to determine the magnitude from the distance and the amplitude. And here, annual occurrence of earthquakes with various magnitude. If it's less than 1, the magnitude, the magnitude, this is the magnitude here, from 2, 3, 4, 5, 6, 7, 9. More than 9, less than 1 earthquakes. Those we call them largest recorded earthquakes. Between, for example, 6 and 7, we have 134 strong earthquakes. Between 3 and 4, we have 130,000 minor earthquakes. So this is just like a list showing you how many earthquakes happening for what magnitude. Comparing damage to structure. So we have two buildings here. This building completely destroyed, this one not. What's the difference? This one built of concrete and this one built of metals. So metals were able to absorb the shock, the wave's shock, but the concrete was not able and then destroyed. Here we have liquefaction, landslides, and ground subsidence. So this one, liquefaction. If we have a place on Earth where it has loose saturated sand material, okay, below the soil, before earthquakes, the saturated loose sand will be fine, but when earthquakes happen and this loose sand shaked, will be ejected outside the soil and create mud volcanoes, which is just all the sand and mud ejected outside, and then the ground will be settled down and the sand will be more packed and lost most of its sand. If it's water and some of the sand outside, creates sand volcanoes. So this is another feature here, ground subsidence. So we have these layers of sand or limestone, I'm not sure, but and gravel, sand and gravel, yeah, sand and gravel. And below there is a mud or clay layer. When the earthquakes happen, they fracture the sand and gravel layers, and until they reach it to the clay layer, and the clay layer starts sliding and move the whole place down, and this is the destruction that happened in that area. Turn again heights. And this earthquake happened in Japan because the ground was, unconsolidated sediment. And this is another earthquake happened in Alaska in 1964, and caused subsidence. Formation of a tsunami, what happened here? Displacement happened along the ocean. This subduction zone, the oceanic crust went below the continental crust, and then fracture happened, and energy released, and this energy will go through and this energy will go through the ocean, and that will cause waves moving the water, and the water waves will move very fast, very quickly in all directions, and as it goes close to the ocean, it's slow to the shoreline, the speed goes down from 800 kilometers per hour to 340. Slows down, but the waves will be getting higher and higher and higher, and that will be destructive and destroying everything along the beach. This is Japan tsunami. So let's look at the travel time. So South America, the tsunami happened here due to the adjustment of the subduction in the subduction zone. In 1 hour was here, 2 hours, 3 hours. It was so fast to reach to the Honolulu almost in 12 hours. Same thing in New Guinea, it reached it in 10 hours. From Aleutian Islands, it reached it to Honolulu in 5 hours. So fast. Earthquakes of magnitude 5 or greater over a 10 years period. So all these maps showing just earthquakes of 5 and more on Richter scale. Seismic gaps, tools for forecasting earthquakes. We'll go over this. And then here we have paleoseismology, the study of prehistoric earthquakes. Here basically they're studying the displacements of the faults to predict the magnitude of or how many earthquakes happen. Because we know the earthquakes, to release the energy, you need faults. So, the Earth's interior. The time required for P and S waves to travel through the Earth depends upon the properties of the rock material encountered. Based on seismological data, the Earth has been divided into 4 major layers. The crust, very thin outer layer, thin and rigid. Mantle, rocky layer located below the crust. The crust and having a thickness of almost 3,000 kilometers. The outer core, a layer of about 2,000 kilometers thick as a mobile liquid, and it's liquid. The inner core, solid metallic sphere, about 1,000 kilometers. So how did they find that? S waves couldn't propagate through the core. Why? Because the core is a liquid. Therefore, a portion of this region is a liquid. And then they find out P waves velocity suddenly decrease as they enter the core. Since melting would reduce the elasticity of rocks, points to the existence of a liquid layer below the rocky mount. This is the asthenosphere. The last major subdivision of the Earth's interior was predicted by the discovery of seismic waves believed to be reflected from a boundary within the core. Hence the core with a hence a core within a core, so the inner core inside the outer core was discovered. P waves passing through the inner core are faster or traveled faster, have faster travel time than those penetrating the outer core. So the apparent increase in the elasticity of the inner core material is considered as an evidence for the solid nature of the Earth's interior. So let's look at here. So here we got an earthquake, or we sent waves to the Earth's interior. What happened? We have P waves and S waves. We know P waves can travel through solid and liquid. S waves can travel just through solid and cannot travel or transmit through the liquid. What happens? Through the crust, both traveled, and we can record them everywhere. And then when it comes to the mantle, both waves slow it down at the upper mantle because we have a weak, weak zone, which is the asthenosphere, the asthenosphere zone. So we knew there's a hot zone that can flow. It's not completely rigid. And then when we reach it, when these waves reach the outer core, that's when the S waves completely disappeared, and we knew there's a liquid. Also, the P waves slow it down because P waves are faster in the solid and slower in the liquid, but S waves completely disappeared. That was a proof that there was a liquid zone. So that was the outer core. But P waves kept going slower speed until they reached the other boundary between the outer core and the inner core. And that boundary, when the P waves reached that boundary to the inner core, they picked up the speed again and get faster. And that's how we know there's a core inside the core. So we have an inner core inside the outer core. And the inner core is solid. The outer core is liquid. Also, we got another zone, we call it the shadow zone, P wave shadow zone. So when P waves moved from the mantle to the outer core, the media are different. The mantle is hard and the core is liquid, the outer core. So the P waves started bending and gave us this 35 degrees shadow zone. The Moho discontinuity, Moho is a scientist discovered the boundary or the boundary that separates the crust from the underlying mantle. So we call it Moho zone. The shadow zone, we just talked about it, having the P wave, is a belt where direct seismic waves are absent approximately 35 degrees wide, which is the P waves. Okay? The shadow zone is produced by the bending of P waves which enter the core. Good. The zone which exists within the upper mantle is called the asthenosphere. And in the asthenosphere, the velocity of S waves decreased. Yes, indicating this zone consists of partially molten material or molten rocks, like 10%. And then we have the lithosphere, which is the outer solid portion of the Earth. Includes the upper part of the mantle and the crust. And both this lithosphere is directly above the asthenosphere. Here, composition of the Earth. Waves can tell us about the composition of the Earth. The continental crust, which is mostly made of granitic, is quite different. Granitic rocks, quite different in composition from the oceanic crust, which is the ocean floor crust, which is basaltic composition. Some of the lava that reaches the Earth's surface originates in the partial melted asthenosphere, the upper mantle, located within the mantle. The heavy minerals sank during the early history of the Earth. By the same token, the lighter minerals, which is the continental crust, have floated to the top, creating the crust. Thus, the core of the Earth is thought to be mainly iron and nickel. Okay, so here's the inner core, outer core, and mantle, and the mantle divided to outer mantle and upper mantle. If we look here, and then we have the crust. If we look here, we'll find from the upper mantle. The upper mantle, we have here the asthenosphere, and then the uppermost mantle, the asthenosphere is this hot, weak, rocky layer, like 10% molten. And above the asthenosphere, there is a lithosphere, which includes the very uppermost mantle and the crust, either oceanic or continental. So this explains the Earth is not homogeneous, heterogeneous, and have four main shells: inner core, outer core, mantle, and crust. Take-home message: earthquakes and Earth's interior. The mechanisms, or what mechanisms does produce destructive earthquakes? Crustal uplifting, subsidence, and horizontal movement. And then we talk about seismology, seismographs, and seismograms. And the two main groups of seismic waves: surface waves, body waves. Body waves can be divided into two waves or two types: primary P waves, secondary S waves. And then we talked about waves, uh, uh, waves of propagation or waves of travel. Sorry, methods of travel or waves travel. And we find out P waves, they move as push and pull or compress and dilate. And S waves, they shake particles up and down in direction of propagation, in their direction of propagation. Location of earthquakes, we find them by using the distance to the epicenter from three different seismic stations. Earthquakes, intensity and magnitude, we talked about this for Richter scale. Earth's interior, waves, P waves and S waves told us there are four layers or four shells: the crust, the mantle, the liquid. The mantle solid, the outer core liquid, the inner core solid. And then we talked about Mohs discontinuity, the shadow zone due to the bending of the P waves, the asthenosphere, the hot, partially molten zone, lithosphere, hot, rigid zone, and then composition of the earth, continental crust, granitic rocks, oceanic crust, basaltic rocks. And by this, we conclude the lecture, and we'll come to a 3 minutes rest with the national anthem of Cyrenaica state. Thank you very much.